Okay, thank you for the introduction. I will talk about 3D volume navigator-based prospective motion correction in CEST MRI. But first, I would like to introduce about the basics of CEST MRI and the challenges of acquiring CEST MRI. And I will talk about the effect of motion on CEST MRI and our methodology and results and discussion. So chemical shift is the basis of CEST MRI. We all know that protons of different molecules experience different range of magnetic environment and shielding effect from the surrounding electrons. Due to this, different molecules will have a different Larmor frequency. So this frequency distribution allows us to selectively excite specific molecular protons without exciting other molecules. So CEST stands for chemical exchange saturation transfer MRI. It is a new contrast method. It is an indirect measurement of metabolites or molecules with a small concentration which cannot be detected using the standard MRI technique. In CEST MRI, a long saturation pulse is applied to selectively saturate protons of molecules that we want to detect, and these protons will exchange with the water protons or water pool. So if we take a normal water signal measurement, the water signal will reduce due to the transfer of the saturated protons to the water pool. So what's measured in CEST is a relative measurement. We acquire a signal without saturation, without applying any saturation, and we acquire another signal by applying RF pulse, long RF pulse, to saturate specific molecules that we want to detect. And we can compare these two images and we will get the indirect measurement of these molecules that we want to detect. So ideally, we need two measurements, one measurement without saturating and measurement after applying RF pulse. So it will take a total of 4 seconds. But things are not that much easy. Saturation is not the only effect that affects the water signal, but semi-solid macromolecular molecules also may exchange their magnetization with the water molecule by a dipole-dipole interaction, and the water resonance frequency is not perfect. The RF radiation that's centered on the metabolic resonance also may affect the water signal, and it may directly reduce the water. So the signal that we acquire will be a function of the CEST, which is the molecules that we want to detect, and the MTC, as well as the direct saturation effect. So to get rid of this effect, instead of taking a single measurement by saturating these molecules, we can apply another saturation pulse at opposite spectral location. So assuming that this MTC and the direct saturation effect are symmetrical about the water frequency, at the positive chemical shift, the signal acquired will be a function of CEST, MTC, and direct water saturation, but at the opposite spectral location, the signal acquired will be a function of only MTC and DS effects. So if we take the difference of these two signals, we will get the CEST metric, which is MTR asymmetry or magnetization transfer ratio, and this will be the CEST effect, totally the CEST effect, and this will give us information about the molecule. So we can trace the molecule by drawing the CEST curve, and in this case we will need 3 measurements. One measurement at the saturation frequency at opposite spectral location and without applying any saturation, and it will take a total of 6 seconds. But these molecules doesn't have a specific a specific resonance frequency. Rather, they will occur at a range of resonance frequencies, so we need to acquire multiple measurements. By acquiring multiple measurements, by applying different saturation pulses, we can acquire the Z spectrum, and a dip on the CEST signal or Z spectrum or a peak on the MTR asymmetry curve will give us a detection of a molecule. You can say some molecule at this resonance frequency is detected. So this will make the acquisition time long, and the long acquisition time will make the CEST more susceptible to motion. Occurrence of motion will cause amplitude change, shift in offset frequencies or chemical shift. False dip or false peak also may be introduced due to this motion. On this picture, you see the detection of APT and amine on the white matter and gray matter. This dip indicates a detection of molecules. The same curve may look like a detection of this APT or amine, but it is totally due to motion. So a motion on CEST may lead to misinterpretation of the data. The traditional method to correct motion in CEST totally depends on post-processing technique or curve fitting technique by applying interpolation. But applying interpolation is not convenient. It's not feasible, or it's not possible to identify whether the dip is due to motion or due to detection of molecule. So the aim of this study is to optimize the CEST sequence by incorporating volumetric navigators to correct for motion in real time. So generally, the CEST sequence have two parts. One, the saturation pulse. Most of the time, long continuous wave saturation pulse will be applied, or a series of pulses will be applied. This determines the type of image contrast, and the other is the imaging part, which determines the resultant image quality. So we modified this CEST sequence by by inserting navigators before the saturation pulse. So the navigators have around 300 milliseconds. Since the CEST have a 1 second gap for the spins to return to their original position, the navigator doesn't need any additional time. We just use the gap to insert the navigators. So to validate this technique, we performed 4 kinds of scans. CEST scan with no motion and no motion correction, CEST scan with motion and no motion correction, CEST scan with no motion and motion correction, and CEST scan with motion and motion correction. The scanning protocols used were for the navigator. Low resolution images were acquired with just 2-degree flip angle. For the CEST, 1 microtesla saturation power, where long saturation power was applied, and 43 of CEST scans were acquired between -5 and 5 parts per million with respect to water. So the first test we did was to check whether the navigator have effect on the CEST signal and vice versa. So we plotted the CEST spectrum for both the navigator and the CEST scan. So this blue curve indicates the navigator data throughout all of CEST scans. So as you can see, the CEST doesn't have that much significant effect on this navigator. And also this red line indicates CEST without the navigator, and the green indicates CEST with the navigator. So both look like the same, so adding the navigator doesn't have effect on the CEST. So this is a signal acquired without applying any motion. And after introducing motion, intentional motion during the scan, these false peaks are detected, false dips on the CEST curve, and false peaks on the emitter asymmetry curve. After applying motion correction, exactly the same signal was achieved. We overplotted this to compare the no motion correction and after motion correction, and both look like the same. For some reason, if someone don't want to apply the navigator, he can use information from the motion parameters to see where the motion occurs and apply the post-processing technique. So in conclusion, the proposed technique allows for real-time motion correction for the CEST scans with no additional scanning time. This allows accurate CEST data analysis. In the future, since the CEST scan is based on the chemical shift, it is very sensitive to magnetic field inhomogeneity, so we will incorporate another navigator, which will make it double volumetric navigator, tells us a sequence to simultaneously correct both the B-node change and the motion in real time. And finally, if I'm allowed, I would like to say Happy Ethiopian New Year to me. Tomorrow will be September 1, 2010. It's not 2070 in Ethiopia. And today is neither August nor September. It is Pagame, we call it Pagame, which is 5th of Pagame, which is a certain month. All Ethiopian years have 30 equal number of days, like the Gregorian calendar, which shifts. So we can say the Ethiopian year is motion corrected. Thank you.